This video is the first video on the application of diodes being used to do what's called rectification. And rectification is when you convert a signal that doesn't have any zero average, or excuse me, it has a zero average. And another way to phrase it is that it has zero DC value. Okay, DC value and average value are the same thing. So rectification takes a signal that doesn't have any average value or DC value, and it converts it into a signal that does have average value, so therefore does have DC value. And here's a rectifier circuit where we have an AC input signal. Here's our diode, and then here's the output across this resistance. And we're assuming in this talk here that the diode is ideal. Okay, so this is an ideal analysis. So, as you know from your circuit theory, when you have an AC source like this, during the positive half cycle, the polarity across the source will be like this, where the higher end voltage is at the top of the source symbol and the lower end voltage is at the bottom of the symbol. So, as we learned previously, well, current wants to flow from the higher end to the lower end through the circuit like this, and as we learned previously, current will only flow anode to cathode through the diode. That's our forward bias current. So as this current's flowing plus to minus of the source, it's passing through the diode anode to cathode. So during this entire positive half cycle, this diode's going to be forward bias. So you see during the positive half cycle, the diode is forward bias, and ideally the forward bias diode acts like a short, and that means V out will just equal the input voltage. So across this resistor will be the same half cycle that we have at our input. Now during the negative half cycle, and we'll put a different color for this, during the negative half cycle, the polarity across the AC source will reverse. Right now the higher end voltage is at the bottom, the lower end voltage is at the top. So now current wants to flow like this direction, right, from the higher end of the source to the lower end of the source. But to do that, it would have to go cathode and anode through the diode, which, as we've talked about, the diode won't allow it to happen. So the diode is reverse bias. So during the negative half cycle, the diode's reverse bias, it acts like an open, therefore it disconnects the source from the output. No current flows through this resistor, so our output is just going to be 0. 0 volts. So effectively what happens is at the output, the positive half cycles are allowed to pass through the diode when the diode is forward bias, acting like a short, and the negative half cycles are not allowed to pass through the output since the diode's acting like an open and it disconnects the source from the load. So what we end up with is that if our input looks like this, well, our output is just going to be the positive half cycles. And if we were to reverse the orientation of the diode, okay, if we were to keep this circuit the same source, same resistor, but now we flip the diode, so the cathode's over here and the anode's over here, well, in that case, the positive half cycles would be blocked from passing through to the output, and the negative half cycles would be at our output. So by just simply switching the diode orientation, we can get the other part of the sinusoid at the output as opposed to the positive cycles in this particular case. But in either case, what happens now is you've converted this input signal that has an average value of 0. Okay, because as you know, sinusoid, no, I didn't draw it as symmetric, but just imagine that this is a symmetric sinusoid. Well, the positive areas cancel out the negative areas. Okay, so our average value is just what this is centered on, and since it's centered on 0, we would have an average value or DC value of 0 volts. But now at the output, since the negative cycles have been lopped off, if you will, we only have these positive areas. So if we find the average value of this, right, and the average value is just 1 over period the integral of that function. And this is shown on Polylearn, so I'm just going to refer you to Polylearn to look at the details. Okay, and what you'll see on Polylearn is, you know, if we call this peak here A, okay, so A is just the peak voltage. Well, it turns out that the average value of this rectified signal is just that peak voltage A divided by pi. Alright, so by just passing that signal through the half-wave rectifier, we've taken this symmetrical sinusoid with an average of 0 volts, and at the output we now converted it to a signal that does have average value. Okay, again, that can be calculated with this equation. Now, often in a half-wave rectifier, in addition to the diode and the resistance, you'll have a capacitor. And the function of that capacitor is to smooth out these humps, if you will. Okay, the half cycles that were allowed to pass through to the output, the capacitor is going to have a tendency to smooth these out. You might remember from your circuit theory that one way to think of capacitors is that capacitors act like shock absorbers to voltage. Right? Voltage can't change quickly across a capacitor. It's going to have a tendency to smooth it out since it takes time for that voltage to change. And you see, when this diode becomes an open, when it's reverse bias, this capacitor is going to discharge through the resistance at the output. And if we make this RC time constant a large number, so it discharges slowly, well, it's going to effectively flatten out these humps. Because right here on the initial upslope, the capacitor is going to charge, but then as it starts to discharge and the diode becomes an open, it discharges slowly, and the slower it discharges, well, it's going to flatten out these humps. And what you've effectively done is you've increased the area underneath this curve, so therefore you've increased the average value. You've increased the amount of DC volts that you have at the output. Okay, so the purpose of this capacitor is to increase our average value, you know, more than we would get with just the diode without the capacitor. See, this is the signal here without the capacitor. This is the signal with the capacitor added. Now, as far as for testing purposes, I expect you to know this equation here. There is an equation in the book that you can use to find the exact amount of voltage you have when you add this capacitor. I'm not going to hold you to that equation. I just want you to understand conceptually that the capacitor does this, that it just increases our DC volts at the output compared to what we would have in this case. And if you think about it, what's occurring here is that we're taking an AC voltage and we're approaching, you know, with this capacitor at the output of the rectifier, we're approaching a pure DC. See, this is sort of like a bumpy DC. It's not completely flat like a pure DC would be. But you'll see later on in the course that there's a device called a Zener Diode, which is a special kind of diode that when we add to a rectifier circuit, for all practical purposes, we can get a pure DC at the output of that circuit. And that's what an AC to DC converter is. An AC to DC converter is just a rectifier followed by a Zener diode that does something called voltage regulation that we're going to talk about later this quarter. Okay, well, there's another type of rectifier called a full wave rectifier, and we'll talk about that rectifier in the next video.